Great. Thank you so much for joining us tonight in our Passions in Practice series. This is our third event. It's nice to see some of you for the second and even the third time joining us for this. Tonight, really excited to welcome Charlie Atkinson, who is the Chief Engineer of the Webb Telescope. Charlie has, as you can see, a presentation and some things for us to that he's prepared for us, but also there's a Q&A at the bottom. If you guys have questions throughout the presentation, please feel free to add them into that Q&A, into that chat, and I will help Charlie as those come through, sort of pause what he may be talking about at any point and get those answered throughout the course of the evening. So please don't be shy with any questions. And with that, I'm excited to turn it over to Charlie, and thank you so much for being here tonight.
Cool. Well, hello, everyone. Yeah, so I'm Charlie Atkinson. I was a member of the graduating class of 1980 in what was then Governor Dummer Academy. And from there, went to college down in Central Virginia, Western Virginia, small school called Washington Lee University. And then started my career in engineering after that, which is a long story I won't get into. But so, yeah, I did want to share with you some of the history and the story of the James Webb Space Telescope. I call this the Cliff Notes version because Webb was a very, very long program with many little stories scattered throughout its history. And there's no way I could even pretend to cover it all. What I did try to do is cover kind of end to end what happened with Webb over the years. So let's get into it. So let's see, how do we do this? There we go. So it all started with the science objectives. So along about 1995, the National Science Foundation commissioned a team led by Alan Dressler out of the Carnegie Institute to answer the question, what's the most important thing on astronomers' minds? So this was 1995. It was in the middle of the Great Observatories program, which is a program that NASA Science Division put together to study the universe with space telescopes that looked across the electromagnetic spectrum. So there was the Compton Gamma Ray Observatory that had been up and did some great stuff. There was Hubble, which operated in the UV, visible, and near infrared. It was launched in 1990. Corrective optics were put into it in 1993. So there was about 2 years of science behind it at this point. There was the Chandra X-ray Observatory, which was being assembled at that time, and the Spitzer Infrared Telescope, which was also in the early phases of development. So given all of that science capability, the question was, what's next? What's the next thing that astronomers and the astrophysics community wants to go study, go look at, that is beyond the capability of these four great observatories? So Alan Dressler pulled together hundreds of astronomers and astrophysicists from across the country and across the world, for that matter, to answer that very question. And so in 1996, they came out with this report, affectionately called the Dressler Report, that answered that question. And they had two major science objectives that they came up with. The first one was called the assembly of galaxies. So looking at our galaxy, the Milky Way, our neighbor Andromeda, they're both spiral galaxies. And so what causes galaxies like ours and Andromeda's to look the way they do and other spiral galaxies that are out there? What are the processes that causes them to form in that configuration versus other galaxies? So that was one of the two science themes. And the second science theme was planetary systems and the origins of life, getting to that root question, are we alone in the universe? And being able to take some steps in that direction, not, go actually image aliens, but to go look at other planetary systems and try to understand their atmospheres to see if they are capable of sustaining life. Do they have what are called biosignatures? So is there water in the atmosphere? Is there carbon dioxide, methane, oxygen, etc.? So those were the two science themes that were that came out in this report. And the report said to be able to go do these, you need a 4-meter size mirror, right? 4-meter aperture telescope, and it has to operate in the infrared. So that was in 1996. Then at the American Astronomical Society annual meeting in January of 1997, Dan Golden, who was the administrator of NASA at the time, he was given the keynote speech. And he looked down at Alan Dressler, who was sitting in the front row, and said, "Alan, you were not bold enough. You limited yourself. Don't restrict yourself to fitting a single mirror inside of a launch vehicle. Go bigger, go bolder. Give me an 8-meter telescope." And with that command, that new required capability, if you will, as mandated by the administrator of NASA, that enabled 2 other science objectives. The first one is looking at the very early universe and looking at the light that was emitted by the first stars and galaxies that were formed in the universe. For a very long time, the James Webb Space Telescope was nicknamed the first light machine because of that science objective. And with an aperture, a mirror that's 8 meters, which is what it was originally hoped to be, you could go do that. You could collect enough light from such a distant object that you could actually image it and see it. And then the second added science capability or science theme was the birth of stars and protoplanetary systems. With a very large aperture system operating in the infrared, you see this image down here in the bottom right, how it's kind of murky and muddy. With there are stars forming in there, and there are planetary systems forming, but you can't see because of all that dust. But in the infrared, you can peer through that dust, and you can actually understand the processes of how planets are formed and what causes their, or what is the process that determines whether you get rocky planets like Earth, Mars, Venus, Mercury, versus getting the gas giants like we have in the outer portions of our solar system. And do you tend to get more rocky planets? Do you tend to get more gaseous planets? Is it a mix? So try to understand all of that. So those were the 4 basic science objectives. So those objectives then drove the architecture for Webb. So if you want to go see the earliest, faintest galaxies, and you want to go look at nearby planetary systems beyond what Hubble can see, then you need, number one, that large mirror, right? That large mirror gives you increased sensitivity, more photons because you got a big collecting area. And it also gives you more detail because the angular resolution is proportional to the diameter of the telescope. So we actually have a 6.6 meter telescope. And so you get much better resolution as a result of that. It has to be infrared because if you want to see distant galaxies, because the universe is expanding, very distant galaxies are moving away from us at a very rapid pace. And therefore, the wavelengths of the light that they're emitting get stretched into the infrared. So you need to be able to have infrared capability to be able to observe things that are very, very far away. And also, as I said, to peer through the dust, to be able to see what's going on as stars are being formed and planetary systems around them are being formed. And if you're going to be infrared, you got to be cold. Heat is infrared emission, right? And so you don't want your own emissions to swamp what you're trying to observe. So you need to be really, really cold to avoid that. And then you need to be ultra stable so that you can take these very long exposures so that you can see these very distant objects. So those are the architecture drivers for Webb. And so this is kind of a real simple breakdown of what Webb looks like. Sorry, pause to get a sip of water. So on the bottom of the image here is the warm side. This is always facing the sun, and the Earth and Moon are always on this side of the observatory. And then on the other side of the sun shield, is the cold space-facing side. And so that allows the cold side to passively cool to very, very cold temperatures. So there's the big telescope with its 6.6 meter mirror made up of 18 super lightweight mirror segments. They're all supported on an ultra stable structure, and it's diffraction limited at 2 microns. And if you don't know what that means, just suffice it to say it's got very good imaging capability. Over to the left of that, the science instruments, that's colored green because that was provided by Goddard Space Flight Center, NASA. Everything else that you see in here was provided by Northrop Grumman and our teammates. So 4 science instruments that we're able to observe from the very edge of the visible into the deep red of what you and I can see, all the way out to the mid-infrared, and had the ability to do imaging and spectroscopy. I'll talk a little bit more about that in a bit. Then there's the spacecraft. That's where all the housekeeping is done. That's where the communications system is, power coming from the solar array, the command and data handling system, data storage, etc. There's a nested pointing control system that gives very, very precision pointing accuracy down to 7 milliarc seconds. Propulsion, we were originally making sure that we had enough propulsion for an 11-year lifetime. With the fantastic launch that we got from Arianespace, we're actually projecting out to more than 20 years of life in the propulsion and what we've got on board. And also a vibration isolation system to keep the disturbances in the spacecraft from disturbing the pointing and stability of the telescope. And then that sun shield. The thing's the size of a tennis court. Its 5 layers allow the telescope to passively cool by dumping heat out to space down to 45 Kelvin, 45 degrees above absolute zero. And that is enabled by this very complex deployment system that I'll talk more about later. But there are 90 cable-driven deployments and over 100 release devices associated with that deployment. So very complex system. So that's JWST in a nutshell. To make JWST work, there were 10 brand new technologies that had to be invented for Webb. I could spend an hour talking about each one of these, but I won't do that. There have been papers written on all of them. If there's any particular interest in any one of them, let me know, and I can delve deeper. But they're starting with in the upper right with the beryllium primary mirror segments. They had to be extremely lightweight. The Webb telescope primary mirror, as I said, is 6.6 meters in diameter, compared to the Hubble mirror, which is 2.4 meters in diameter. So 7 times the collecting area, but 1/10 of the mass, 1/10 of the weight. So they had to be very, very light. Each of those mirrors sat on the structure behind it, but because each of those 18 mirrors are on that structure, if that structure moves at all, then effectively the primary mirror bends and changes shape, which would then degrade the image quality. So that structure had to be extremely stable. Cryogenic ASICs had to be brought to bear to read out the electronics, to read out the focal planes. The detectors, both the near infrared and the mid infrared, increased sensitivity over what had been done before, increased pixel count for better spatial resolution. The mid-infrared detector, because it looks in the mid-infrared, needs to operate about 6 Kelvin. So a cryo cooler was needed to bring the temperature down to 6 Kelvin. Cryogenic heat switches to engage the radiators to dump the heat from the instruments. And then micro shutters. Oh, these devices are cool. They're an array of these little 100 micron by 200 micron shutters that can open and close. And there's an array of them that's about 1 million of those little bitty shutters. And the way they work is you take a line of them and open them up, and you create a slit when you do that. And you put the image of a bright object where that slit is, and it creates a spectral spread behind it that you can then, put out on a detector, and you can see how much of what wavelength that image contains. And so you can get spectra of a particular object, be it a planet or a star or whatever you want to look at, through that process. Now, the way they used to work is you would go point at a telescope at an object, get the object's image to go through that slit, get its spectra, check, go on to the next one. Well, with this microshutter array device, you can open up slits as many as you want. You can open up 100 of them. And so with one collection, you can collect spectra from 100 different objects, which really increased the science utility of Webb over what was done previously. Anyway, I love those things. Then there's the sun shield membrane. That was new technology that had to be brought to bear. And then the process for taking the telescope, once it was unfolded, once it was deployed, taking it from that state to a fully aligned and high quality telescope, that was a whole process that kind of had to be invented. How do you determine what the alignment state is of each of those 18 mirror segments? How do you determine the alignment state of the secondary mirror? And then get them back into alignment so that you can get the pristine imagery that we want to get with Webb. And you'll see more of that coming up. So, okay, we now had our technologies, we got our architecture defined, got our science objectives defined. Let's go build some hardware. I just randomly picked some different pieces of hardware across the observatory and from across the United States to put here, but obviously there's a lot more to Webb than just these 5 things. But by way of example, there was the mandrel for the cone and the spacecraft bus that was built down in San Diego. In the upper right is the 18 mirror segments that make up the primary mirror. These are the shipping containers. You can't see the mirrors themselves. They're inside those shipping containers to keep them clean. Up in the upper left is the solid. No, those were finalized in Colorado, by the way. In the upper left is the solid state recorder. That's where all of the science data goes and gets stored before it gets downlinked to the ground. On the bottom left, there's some of the structure that supports the mirrors. These are the 2 wings on each side of the primary mirror. Each of those supports 3 of the primary mirror segments. Those are built up outside of Salt Lake City in Utah. And then the center is the sunshield membrane. This is one of the flight sunshield membranes. I think this is layer 5. And that was built up in Huntsville, Alabama. So just an example of some of the hardware that was produced for Webb. So next up, we got all this hardware. It's time to put it all together, one piece at a time. This is a time-lapse video of the integration of the mirror segments onto the backplane structure. There's a little bit of music that you're hearing in the background. Hopefully it's not too loud. Anyway, what you're seeing, you're probably asking, well, hey, those don't look like mirrors. They're not shiny. And they should be gold colored, but they're black. What you're actually looking at is the contamination cover that was put on each of the mirrors to keep dust from collecting onto the surfaces of the mirrors, to minimize the amount of transmission loss that we would get as a result of contamination. Each of the mirrors was picked up in that robotic arm, brought over to its location, put in place and held in place while it was precision aligned in 6 degrees of freedom using that robotic arm. And then once they were happy with where it was in alignment, they ground the shims for it, put the shims in, shot the glue in and let it cure overnight, and then moved on to the next mirror. Took about a month from end to end to do all 18 of them. But at the end, we had all the mirrors installed. After the mirrors were installed, we put the instruments in. Whoops, don't do that. Go to the next one. There we go. We put the instruments on the on the back of the telescope and then shipped it down to Houston, Texas, down to Johnson Space Center to do a performance test. This is Chamber A down at Houston. It's the chamber that was used to test the Apollo landing module. And we had to completely revamp it, turn it into a clean room, put clean room blowers on the inside of the chamber, change out the thermal shrouds so it could get down to near absolute zero. So we emulate the temperature environment for the telescope, and then put a whole bunch of optical metrology inside it so we could verify the performance of Webb. We wanted to make sure it was going to work the way we expected at cryogenic temperatures before launching into space. So after we got done with the test down at Johnson, we sent the telescope up to Redondo Beach, where we integrated it with the spacecraft and the sun shield. And I did not want sound. Let's see if I can turn that off. Okay, cool. So yeah, bring the telescope over, lower it down onto the spacecraft and the sun shield, and then went through the process of deploying the sun shield to make sure it worked correctly after that integration was complete. You see each of the 5 layers being separated and the final tensioning of the membrane. And at that point, we had a fully integrated observatory. Once we had the observatory fully integrated, checked out the deployment, it was time to bring it over and do environmental testing on it. So picked it up from where you saw that image previously, bring it over to the transporter in the left-hand part of the clean room here, and then put a contamination cover around it so that the telescope stays as clean as possible while we transport it outside over to another building. In the photo on the right, that's the acoustic test chamber that we use for testing large systems like Webb. You can't see the large speakers that we've got in here, but they're about 6 to 8 feet tall. The woofers are anyway. And we energize them to expose the telescope to the kinds of acoustic environment it's going to see during launch. Launch is a very, very violent process that includes disturbances acoustically and vibrationally. We want to make sure that it will survive that before we actually hit the big red button and launch it into space. So we subjected it to an acoustic test. When we finished that, we brought it out and over to our vibration test facility. You can see there are 2 different platforms here. The one in the front provides a vibration, what we call a base shake, from left to right and in and out. And then the plate in the back provides the other axis up and down. So between all 3 of those, it gets a full 3-axis vibration, subject the telescope to the full set of environments that it'll see during the launch campaign. Again, to make sure that when it is done with all of that, it will still operate the way it needs to. So after the vibration test, take it out of the vibe facility, bring it back over to the high bay, take the contamination cover off, and put it back up on the test stand, where we did another deployment test of the sun shield. You see it in the deployed state here. And then do a deployment test of the wings to make sure that they deploy correctly. This was the final test of the deployments on Webb before it was put into space. But more importantly, it was the final stowing. Here you see the sun shield being stowed. This is the last time it'll be put in the stowed condition. So that operation was critical to make sure it was done correctly. We then brought it out from Redondo Beach and brought it down to Seal Beach, which wasn't too long of a drive, but when you're going 5 miles an hour, it takes forever. But then we put the web in its shipping container on a barge that then went down through the Panama Canal and over to French Guiana. And you see it coming out in the port there at French Guiana, which is where Arianespace has their spaceport facility. And then here you see the encapsulation process where that launch vehicle fairing gets put over web. That's that same fairing that can only fit a 4-meter mirror inside of it, unless you cut that mirror up into pieces and stow it. Then the launch vehicle went out to the launch site at the spaceport. And then on the morning, Christmas morning of 2021, Arianespace launched Webb on its journey to the second Lagrange point, 1,000,000 miles from Earth. It's a pretty spectacular day. Good day for a launch. The really cool thing is, after the launch was done and we're separated from the launch vehicle, which you see here, there's a camera that was on the upper stage, and we're actually able to visually see the solar array deploy, which to me was awesome. It means, yes, first deployment successful, we're able to get power from the vehicle. Then what you see here is what happened on the way to the second Lagrange point with the deployments, starting with the sun shield, the pallets that contain the membranes, fold them out, and we separate the telescope from the spacecraft and the sun shield, and then pull the membranes out via the mid booms, and then go through the process of separating the membranes of the sun shield. Each of the 5 layers individually stepped up through each of the spreader bars, the 6 of them there, and then tension it. And then finally, the last deployment was the 2 wings of the primary mirror. The process took 14 days. I refer to it as the longest sigh of relief I've ever had, because each day that we were successfully able to complete another set of deployments was just one more bit of relief. This next video, I'm going to do a little setup before I play it, because it goes really fast. And it's not always easy to understand what's happening. So I'll do my best to explain what you're about to see. This is the process that we went through. You know, we're up now, we're launched, we got the telescope deployed, but it's not aligned. So each of those 18 mirror segments are pointing somewhere. Secondary mirrors somewhere else. You know, we knew approximately where they were going to be. We had, you know, deployment capabilities that got, you know, within reasonable tolerances, but we knew that it wasn't going to be aligned. And as I said earlier, we knew we'd have to go through a process to align it. And we developed a process using images from the science cameras to be able to do that. And so the process starts with finding the mirrors, right? You need to find each of the 18 mirrors. So did a little raster scan around, locate all of the 18 little blobs of light. Once we identify them, and once we find them, we have to identify which one is which. So move an actuator behind one mirror, see one blob of light move, and okay, that mirror is associated with that blob of light. And then we bring them all into an array. You'll see what that array looks like. It emulates the 18 mirror segments, so we could keep track of which mirror was which. And then we went through a preliminary alignment process by moving the secondary mirror in and out of focus. And we used that information to adjust each of the mirror segments to clean up the image from each of them. And then we went through a process that we called multi-field. So you'll see the image move around to the corners of the focal plane, the corners of the field of view that you see here, because that gives us information about the alignment of the secondary mirror. So we use that information to tweak up the secondary mirror alignment. It actually didn't need much tweak. So you won't see much of a difference. And then we went through a process called image stacking. So we got these 18 blobs of light and we put them on top of each other. And we use that information. So they're on top of each other, but they're not phased. So we're not getting a pristine image. We basically have 18 telescopes stacked on top of each other. And we go through a process called fine phasing. So we put in into the optical train weak lenses that give us a known amount of defocus. And by interrogating the changes in the image as a result of those, we're able to make estimation on what the errors are that we're seeing and make alignment adjustments based on that. And then the final step that we went through is what we call course phasing, even though it was at the very end of the process, because we still didn't necessarily have adjacent mirrors in the 18 mirror ensemble that make up the primary mirror. We didn't necessarily have adjacent mirrors phased, right? So they weren't necessarily stepped with respect to each other, so that you're making up one smooth surface. And so we had a process to create an interference pattern between adjacent segments using a special device that we inserted into the optical train. And the magnitude of that interference pattern defined what the step size was between adjacent mirror segments. And we're able to use that information to essentially get rid of that any steps in between the mirror segments. So I'll go ahead and play it and try to narrate as we go through it. So here, okay, find each of the mirrors, identify them. You see 18 blobs of light. We go through the secondary mirror adjustments and we're able to tweak it up a little bit. And we go through image stacking and make another adjustment, and then put them out in the array again and do that multi-field that I described earlier. So now we can align the secondary mirror. And we do what we call an inverted multi-field. So we go on the other side of focus with the secondary mirror and run through that process again. And tweak up the alignment of the secondary mirror as a result of that. And then once we've done that, go back through and through the same process to verify that we did it right. So now we've got the secondary mirror aligned. We go through another process to tweak up the individual mirror segments alignment. You can see that each of the blobs got a little bit sharper. And now we go through image stacking again. And here's where we're inserting those lenses. And this is the final step of course phasing. And that was the first course phasing. Then we did the image stacking again and the lenses being inserted. And then here is the final course phasing. And you can kind of see that there's up in the upper left, it's light, then there's a little band of dark, then light, then dark. That tells us that, yes, we've got them phased with respect to each other. Let's see if we can. And so this was the first image that was taken with the telescope once the alignment was complete. You know, we gone through the process. We were using that bright star you see in the center there as the image we would be looking at, or the star source that we'd be looking at for doing the alignment. And we got all done, did measurements on that to make sure. And somebody said, hey, guess what? That's the first image of the fully aligned telescope. That was kind of a nice aha moment. Usually when I'm doing this presentation or something like it, I bring this image up, I'll ask the audience, how many stars do you see in this image? And the answer is either 1 or billions, because that bright thing in the middle is a star, but everything else you see are galaxies. So then after 20 years of getting JWST designed, built, and commissioned, it was now ready for science. And this was 6 months after we launched, done all the commissioning. And I refer to that moment as handing over the keys. You know, the engineering was done, the Um, all the effort to get it commissioned and operable was done. And it was time to let the astronomers and astrophysicists to use it as a tool to go investigate all kinds of cool things about the universe. What I did is I pulled down just a couple of images that JWST has taken. I'm sure most people on the phone are familiar with this one. This is the Carina Nebula. This was actually put on up in Times Square in New York City shortly after it was released, and because it's beautiful, it's absolutely gorgeous. But the cool thing about it to me is the science that's going on. So you see, there's an edge there between the dust, the orange stuff, and then the blue background in the upper part of the image. Each of those stars that you see up there, those are new stars. They've just been formed, and they're I'll call it solar pressure, but it's not from the sun; it's from these stars. But the pressure from the photons that they're releasing is pushing that dust cloud. And so that's what you're seeing. Is you're seeing the effect of that photon pressure on the dust cloud. And the cool thing is, if you look kind of in the center, you can see kind of bands of the dust, as that pressure is causing these vertical bands to occur. So just really interesting process in the formation of stars and how they interact with their environment. So it's not just beautiful.
Charlie, I'm sorry to interrupt, but I have a question from a student who's asking what the name of that star. And it might be from the previous slide of
that one. I'm assuming that's the one that's being asked about.
Yeah.
And I don't remember, but it's got a really, really ridiculous name. It's M something something something. So it's in the star catalog. But the reason it was selected, so it's very non-exciting name, unfortunately. But the reason it was selected is because it's a lone star in a field. We wanted that to be able to do the alignment processes, because with just a single star, it's a lot easier to go through all that process I just talked about. I can find the actual name, but again, it's M and then 4 digits. Okay, and then Jupiter and Neptune. I like the image of Neptune over on the right because you can see the gas around the planet itself, which was really, really cool. I'd never seen an image like that of Neptune, and that captures the atmosphere, which is very, very thin and almost looks like it's dissipating. And then the image on the left, Jupiter. I mean, everybody loves the images of Jupiter. What I really appreciate about this one is we're able to clearly see the auroras on the north and south pole of Jupiter. And then JWST's first deep field. One of the most iconic images from Hubble is the Hubble Deep Field, where they took Hubble and basically opened the shutter and stared into a dark spot of the sky. The ultra deep field, which was the second one, was like 4 weeks in length. For Webb, this was about a 3-hour exposure, whereas the scientist friend of mine who wanted to go use this one as one of the early observations put it, I got up in the morning, turned on JWST, went and made myself a cup of coffee and a sandwich, and came back and it was done. It's a little bit of an over exaggeration, but I love the description of it. This would have taken 12.5 days for Hubble to collect. But there's a lot going on here. In the center, you can see there's like a little bit of fuzziness in white light in the center. That's actually a galaxy cluster right in the middle of that image. And the gravitational force caused by that gravity cluster, that galaxy cluster, bends space-time so that it bends the path light, the light path around it. creating a lensing effect, which actually enables us to go see further away and therefore further back in time behind that large gravitational force. And that's how the earliest galaxies have been discovered. In this instance, they were able to detect a galaxy that was older than any that had been detected before. And this was just the first deep field look during a 3-hour exposure. So just amazing, amazing, cool stuff. And the other thing just to note, the only stars that you see here are the things with that diffraction pattern, with that 6-folded diffraction pattern. Everything else you see in here is a galaxy. So there's just trillions of galaxies out there. Stephan's quintet. I think this is a beautiful image. This is the merging of 5 galaxies. The 2 in the middle you can see are definitely coming together. The star centers are very, very close to merging. And you can see the galaxy above those 2 in this image. The gas around that galaxy is being significantly impacted by the gravitational pull of the other 2. So just really, really, really cool image. And then exoplanets. This is just one of many of the observations Webb has done in looking at spectra of planets around other stars. This was one that's in the TRAPPIST system. And by looking at the spectra of that planet with the coronagraph, they were able to detect water, but they were able to distinguish different forms of water by the width of the spectral response. So they're able to detect that there's water vapor in the atmosphere, so clouds. There's liquid water on the surface, and there's also ice. And so they're able to determine that there are all those forms of water on this one planet. And then this is a comparison of the same spot in the sky with the Hubble image and Webb image. Hubble had discovered that there is a galaxy behind this galaxy cluster. Because of gravitational lensing, it actually shows up in 3 locations in the image. But it is the same galaxy that, because of gravitational lensing, it shows up in those 3 spots. But the cool thing is, Hubble had made this discovery, or scientists had made the discovery using Hubble. But when Webb went and looked at it, they determined that it's actually not 1 galaxy, but 2. And one of them is significantly older than the other. The one on the right is older than the other one. And that one, it turns out, was about 4 million years after the Big Bang. And then the pillars of creation, this is in the Eagle Nebula. It's a pretty famous shot. You see on the left side, that's the image from Hubble. And the image on the right is the one from Webb. And you can easily see on the left, it's hard to see what's going on because of all that dust. But the image on the right with Webb, with the infrared detection, you can actually see through that dust and see the processes that are involved in the creation of new stars and planetary systems around those stars. And I wanted to end with this. JBST was a huge program lasting many, many years with contributions from all over the globe. And here you see the location of the contributors. This is within the United States and then Canada, and also from Europe. There were in total 14 countries that contributed to Webb, 29 states within the United States, and over 400 companies and 300 agencies and universities that all contributed to Webb. So I purposefully tried to get this done with time left over for questions. So feel free to ask anything you want.
So Charlie, I've been sort of monitoring the chat, and there's a couple of people who have asked about space debris. What sort of how was the telescope protected from space debris, or what kind of effect did that have on the Webb telescope?
Yeah. So space debris, in my mind, come in two categories, right? In low Earth orbit, you have to worry about man-made stuff, right? Out at the second Lagrange point, it's just what's naturally occurring out there. And people are maybe familiar with the micrometeoroid hit that we took pretty early on in Webb. We had data from Marshall Space Flight Center down in Huntsville, Alabama, on what the environment was going to be like. They had models of what the micrometeor environment looks like. It turns out JWST, with its incredible mirror, is actually the best micrometeoroid detection system ever put into space. That's not what it was intended for, but it's doing a great job of it. So we knew what to expect, and from everything we've seen in the years of operation of Webb, the size and velocity of the micrometeoroids that we've been impacted by perfectly match the models for what to expect. So in terms of their impact, yes, we do see their effect. That big one that hit us, it actually deformed one of the mirrors, but it's just a very localized effect. And so it doesn't really affect science to any noticeable degree. And we had predicted for it. All of our performance predictions were that over the life of JWST, it's going to degrade over time, just like most observatories will degrade in one way or another. And that degradation process is exactly as we expected. It's still performing much better than diffraction limited at 2 microns. Its Poynting stability is still, of order 1 micro or 1 milliarc second instead of 7. And the sun shield, because it can get perforated as micrometeoroids hit it and degrade the cooling capability, if you will, of that sun shield. But we've seen the temperatures starting to slowly climb. So instead of 45 Kelvin, we're at 46 Kelvin. But it's all exactly as we predicted and accounted for. Good question.
Is there a part of the Webb telescope that you sort of consider to be quote unquote yours, that you sort of have more ownership over?
So I started Webb as, you remember the 4 parts of the observatory: the telescope, the instruments, the spacecraft, and the sun shield. I started Webb as the deputy manager for the telescope. So if you break it into 4 pieces, definitely the telescope's mine. If you break it down further, the structure that supports the mirrors is something that I really sunk my teeth in. The deployment of the mirrors was something I really sunk my teeth into early on, and did all the work to develop that technology. So if anything, that's it. But I mean, it's just an incredible machine overall.
Finances. What's the total payload for the Webb telescope?
I heard 2 terms: finances and payload.
The question is, what's the total payload for the Webb telescope?
In terms of, let's see. Let me answer that question in a couple of different ways and see if I actually scratch the itch. So in terms of mass, how much does it weigh? It's 6,500 and something kilograms. So what's that in pounds? That's around what, 15,000 pounds. That's what it weighs. You saw the volume, the size of it. If people are interested in cost, there's not too much I can say about that except for what's been published, and that's the total cost of the observatory was on the order of $10 billion. And that spanned from when we first got on contract, Northrop Grumman first got on contract in 2002 up to launch. So hopefully that answered the question.
A couple of people have asked about sort of the official life service or the life cycle. How long is a telescope expected? What's the lifetime of the telescope, and what capabilities might degrade first?
Ah, great. So first, let's start with the required life, right? So the requirements as that came out of the science requirements document way back was for a 5-year mission life. So that means after launch and after commissioning, the mission life was intended to be 5 years. They then added on to that, yeah, but make sure you got enough fuel to last a total of 11 years after launch, to preserve the capability beyond the original design life. I'm going to segue a little bit and then come back to it. If you look at other telescopes, the great observatories, great example, right? I mean, Hubble was launched in 1990. It's still up there. Now, granted, it had 5 servicing missions to help preserve its life, but none of that was in the optics or the telescope. And the last servicing mission, I can't remember what it was, but it's been probably 15, 20 years since then. So, these observatories tend to last a lot longer than they're designed for. Another good example is Chandra. Chandra X-ray Observatory was launched in 1999. It also had a 5-year design life, but it's still up there going strong. And they're figuring out ways to work around what are degradations in the thermal blanketing for Chandra. But like I said, they found ways operationally to work around that. So similarly, Webb's going to degrade. The life limiting element that we know of today is fuel. Eventually, so what do we use fuel for? So the second Lagrange point is not a stable orbit because you get gravitational forces that change as a result of the moon, as a result of Jupiter even. And so we have to do what we call station keeping maneuvers. So we have to thrust to keep the orbit about, I think it's like 4 times a year. We have to do station keeping thrusts with the propellant to keep it on the orbit. The other thing we have to do is to unload momentum. That huge sun shield is a big solar sail. And the center mass and the center of the solar pressure aren't always aligned depending upon where you're looking in the celestial sphere. So as a result of that, you can build up momentum. And the way we deal with that is we have reaction wheels that we spin. But those wheels, as they spin faster and faster to maintain that momentum, at some point you got to unload them. You got to send them back to zero. And so that requires fuel to compensate for that as you dump the momentum. So we do use fuel, and like I said, the current predictions are a lifetime of over 20 years from the time of commissioning. Exactly how long it's going to be depends upon how efficiently they can use that fuel. But they're taking steps to use it as efficiently as possible. Other than that, I mean, could you have a problem with some of the electronics along the way? Sure. They're designed to be pretty robust, and the way electronics and space systems tend to work is, you go through what they call the bathtub. So it either fails very early or it lasts a very long time before it does fail. So unless something unusual happens, probably don't expect that to be limiting. I think that the next most limiting is going to be thermal degradation, because micrometeoroids will start penetrating the sun shield more and more, and the solar radiation on the first layer is going to start to degrade it, and so we're going to see the telescope start to warm up. And the surface of the mirror is going to start to get more and more little pock marks in it as a result of micrometeoroids. And so we'll start to see some of that degradation, but it's going to be all very, very graceful.
A follow-up question to that would it be possible to use solar energy to extend the life of the Webb telescope?
So we do use solar energy currently. I mean, that's where we get our power from with the solar array. Um, the the result of solar pressure on that sun shield is what gives us that imbalance that we have to then go unload by using propulsion. So it actually works against us, not for us. Now, we can, by scheduling observations in the right way, kind of minimize that imbalance. So we look over here and then we look over there to kind of compensate. But there's still going to be a net reduction in, or net accumulation of momentum that we have to go then dump.
How sure were you that this was going to work, and how scary was it for you in that moment?
Oh my gosh. I did express that 14 days of commissioning was one big long sigh. And that's a pretty accurate description. I was on pins and needles Christmas morning in 2021 when it actually launched. And when I saw the solar array deploy from the camera, it was broadcast on NASA TV, and you could see that solar array go out, and that was a first big sigh of relief. I mean, honestly, let me quote Dr. John Mather, who's a Nobel Prize-winning project scientist on Webb. When he was asked this question once by a reporter, he answered, "We've done everything that we can do on Earth to make sure that it will work on orbit." And, that was kind of in some way, soothing statement that he made, for me at least, because he's right. We could have tested it more, but at some point you start worrying about overtest, right? And creating damage because of the testing you're doing. And the test program that we put in place gave us really high confidence that it was going to work. Now, all that said, there were 344 single point failures on Webb. Hundreds of release devices that all had to work. 50 deployments that all had to behave. A lot of the verifications that we did, we couldn't test because on Earth in gravity, there's some things you just can't test. So we had to rely on our models and do the best we could to validate those models. But there's always some risk. So I had high confidence, but was I nervous? Oh, heck yeah.
How are the targets prioritized for the James Webb Telescope use?
Oh, great question. So let's start with guaranteed time. So there's a portion of time allocated to specific scientists for their observations. There are the people who comprise the science working group. There are scientists in Europe who are guaranteed time because of the contributions Europe made. They provided the launch, right? Free ride to L2. They provided some of the instruments. So there's guaranteed time that they get, guaranteed time that scientists in Canada get, and the guaranteed time that the principal investigators here in the US get. So there's that part of it, and they can do whatever they want. But it's a certain amount of time that they've been given. Then there's general observing time, which I forget what the ratio is, but it's like 70% is general observing, something like that. And there's a whole process that they go through. It goes like this. You think of an observation that you want to make. There's information you can get on the web from the Space Telescope Science Institute, which is on the campus of Johns Hopkins. They have a website that you can get all the information that you need about doing observations, what kind of filters are available in each of the instruments. There's observing time calculators, so you can determine how long your observation is going to take. etc. So you write this all up into a proposal. I want to go look at whatever. That then goes in to um, a TAC, a technical assessment committee, and it's 100% blind. They don't know who the request came from. They know nothing about the requester, and they just evaluate it based upon the merits of the proposal. Is it a unique observation? How much time is it going to take? Et cetera, et cetera. And they make the determination of what will and what will not be observed. And they do it in phases. There are different cycles. I think there are about 6-month cycles that they go through. And, I think the last cycle, they got like 1,300 requests for observations. And for each one of them, they go through that process and make the evaluation and say, okay, here's how much time we have for the next 6 months. Here are the observations that have been selected. They then hand that information over to the operations team at the Space Telescope Science Institute, and they then plan it. They said, okay, well, we'll go do this observation first, and then go do this one second, et cetera. And then all the commanding gets uploaded to go do the observations.
Last question, Charlie. There's more in the chat, but we'll be here until like 10 o'clock tonight. Is the James Webb Telescope ever in the shadow of an eclipse, and what is the impact on its performance?
In the shadow of an eclipse, so when the Earth passes in front of the sun. Well, the short answer is no. And I was starting to think about the impact. The only impact would be we wouldn't have light on the solar rays, and therefore we wouldn't get electricity for a little while, but we've got batteries. So it probably wouldn't be an impact. But the reason that we don't ever see that is because we're not actually at the second Lagrange point. Let me explain what that is real quick. So if you take your two hands and make fists out of them and separate them a little bit, pretend one's the Earth and one's the sun. Well, you can imagine there's a spot in between them where the gravitational pull from each of them is about equal. And so you put something there, it'll just stay there. If you imagine a spot on the other side of the Earth from the sun, that's about the same distance. There's a spot over there that the pull from both the sun and the Earth is equivalent to the centrifugal force that you get from orbiting around the sun. So it's being pushed out with the same force that it's being pulled in. That's the second Lagrange point. But we're not actually at that point. We actually orbit around it in a very large orbit. It's like something like a couple hundred thousand kilometers in size, and what's called a halo orbit. So we're never actually in a position where we'd be in alignment of the sun and the Earth to have an eclipse happen.
Charlie, thank you so much for your time tonight. This was fascinating. Really appreciate you joining us and answering these questions. And as I said, there's many more that were in the chat, and I'm sorry that we couldn't get to them all. Next month, for our Passions in Practice series, Diana Burnell, who's the class of 2000, will join us on Monday, April 28th at 7 o'clock at night. Diana does some nature foraging, and so she will take us on some adventures, and I hope that you will be able to join us. We'll send some more registration material. The recording of this will be also available early next week on our alumni events page if anyone would like to rewatch and sort of learn a little bit more. So thank you again for joining us. Have a great rest of your night.
Bye, guys.